So thank you for inviting me as a speaker for this nice conference. Today I will talk about triangulated categories of locomotives over a field part 1. And tomorrow, Federico Binda will talk about part 2. So the motivation for our project is there are lots of cohomology theories for schemes which are not A1 invariant. So here, many fundamental cohomology theories are not invariant, but fundamental means something which is not derived from the other one. So for example, homotopy K theory is not fundamental in this sense because homotopy K theory is an A1 localization of K theory. So we can divide these theories with 3 types. So the type 1 is A1 invariant cohomology theories, meaning is that Hn of x is isomorphic to Hn of x times A1 for all schemes x, including singular schemes and integer n. Example is like erratic cohomology or Betti cohomology, where L is invertible in OX and X is a variety over C. Type 2 is Hn of x is isomorphic to Hn of x times A1 if x is regular, but Hn of x is not isomorphic to Hn of x times A1 if x is not regular in general. So by equivalent, it is known that K theory is A1 invariant, but if x is singular because if x is regular because we can compare with G theory, but in general, this is not A1 invariant. On the other hand, we can consider Motivic cohomology. So this is a hypothetical cohomology theory, and this is not isomorphic to Voevodsky's Motivic cohomology. So we want these 3 properties. The first one is H2,1 is Picard. Hn, n is Milner K theory if X is the spectrum of a local ring. And 3, we have some Motivic spectral sequence. H p minus q, comma negative q goes to k negative p negative minus q. So, for example, Voevodsky's Motivic cohomology is A1 invariant, but Picard group is not A1 invariant. So 1 is not true for Voevodsky's Motivic cohomology. And 2 is also not true, and 3 is also not true because K theory is not A1 invariant, but Voevodsky's Motivic cohomology is A1 invariant. So type 3, Hn of x is not isomorphic to Hn of x times A1, even for regular schemes x. One example is p-adic cohomology, H et al n x, z p, where p is not invertible in OX. On the other hand, we also have Hodge cohomology as an example. So here omega j may be over k or over z, but both are not A1 invariant. And there are more types of cohomology theories. So HHN, HC, THH, TC, they are introduced by many people, and probably I can say something about the definition of Hochschild homology, HHN. If X is an affine scheme, spec R, then this is a homology of a certain complex R tensor R to R to 0. this is defined by this way in this case, and if R is smooth over a field K, then HHNR is isomorphic to omega R over Kn. And this is due to Hochschild constant Rosenberg. And there are more complicated cyclic homology, topological Hochschild homology, topological cyclic homology. So you may see topological Hochschild homology integral periodic Hodge theory by Bad, Morrow, Scholze, and on topological cyclic homology by Nicholas Scholze for some recent developments. So far, we have seen 3 types of homology theories. So our motivation is there a Motivic homotopy theory of schemes that incorporates these homology theories? So type 2. So type 2 is, for example, Voevodsky, Voevodsky worked with SH of some regular ring, and for this purpose, this is fine. For example, we can define K theory we can represent K theory in SH of K. But anyway, we cannot represent K theory in SH of X if X is singular. And type 3 is worse. That's not representable in SHX even if X is regular. So, and I should say what is the meaning of representability. So the meaning is there does not exist E in SHX such that Hn of Y is isomorphic to hom, Y plus, and sigma Ne for or Y in smooth over X. So goal of our project is construct a non-A1 homotopic enlargement of DMK. The meaning is we want to define some non-A1 homotopic triangular categories of motifs containing DMK as a full subcategory. And we are done if K is a perfect field of resolution singularities. In part 2, construct a non-A1 homotopic enlargement of SHX where X is a scheme. And we have constructed a non-A1 homotopic version of SHX, but it is clear that at this moment that our construction contains SHX as a full subcategory. And 3, represent all cohomology theories in the previous slides. We did some progress, but still many theories, including HC, like THH, are not known to be representable in our category. So before going into our construction of non-A1 homotopic enlargement of DMK, I will review what is the construction Voevodsky did. So there are 4 main ingredients like these. A detail is as follows. Use finite correspondences to form the category of pre-sheaves with transfers. And then form the category of Nisne pre-sheaves with transfers. And then invert A1 to point in the derived categories of sheaves with transfers to obtain DM effective. And then apply pure stabilization to obtain DMK. And for non-A1 homotopic theory, we want to imitate this this construction, but some things should be replaced. For example, we cannot invert A1 to point because we want some non-A1 homotopic enlargement. So to study what is the correct replacement for A1, let's explain some axioms of cohomology theories. So we can say some 4 axioms like A1 rigidity, A1 invariance, P1 rigidity, and P1 invariance. So I0 and I1 are 0 section and 1 section, and P is the projection. So A1 invariance is equivalent to A1 rigidity because A1 is an interval. The meaning is there is a multiplication map from A1 times A1 to A1, but P1 invariance implies P1 rigidity, obviously, and A1 rigidity implies P1 rigidity, but P1 rigidity does not imply P1 invariance. The reason is that P1 is not an interval object, i.e., there is no multiplication map from P1 times P1 to P1. So suppose P1 is an interval object, then we cannot consider P1 rigidity as one of our properties of non-A1 invariant cohomology theories because there are lots of cohomology theories satisfying P1 rigidity but not P1 invariance. So that's quite fortunate. But probably we can force P1 localization, and for P1 localization of cohomology theories, you may see P1 localization with this title by Joseph Ayub. So P1 rigidity is what we want. In P1 invariance is not what we want. And let's consider another viewpoint from topology. So even though A1 resembles the interval 0, 1 in topology, the key difference is that A1 is not compact, but 0, 1 is compact. So even though A1 and 0, 1 are homeomorphic, they are not exactly the same. For example, we can consider some stable homotopy category over A1 and stable homotopy category over 0, 1. But there is no reason to say that SH of A1 is isomorphic equivalent to SH of 0, 1 interval. So topology really sees the difference between A1 and 0, 1 if we introduce 6 functors. An idea is to compactify A1 in a suitable sense. Okay, but there's only one compactification. Like P1 is the only one compactification. But if we just consider separated compactification, but this P1, as we have seen before, P1 is not the right one because P1 is we don't have P1 invariance, and moreover, P1 is not contractible in algebraic topology because that's the Betti realization is the complex projective space. So we want to go beyond the category of schemes. And one idea is just to say like P1 comma infinity. So infinity is considered as a boundary of this one, and this notation is called cube or box informally. And the notation means that we just keep track the boundary. So to form a compactification with boundary, we just need to specify what is the scheme and what is the boundary, and that's it. And this is a compromise notion between non-compact A1 and non-compact P1. So probably we can see these pictures. So we have A1 and P1, and adding an infinitesimal boundary at infinity can be described by the middle figure. So A1 is contractible, not compact, and cube is, but P1 is compact but not contractible, but cube is contractible as A1 and compact as P1. So that's the topological reason why this cube is nice. And on the other hand, as I told before, an algebraic reason is that we don't have P1 rigidity, we don't have P1 invariance, we should not have P1 invariance, and we should not have A1 invariance, and we have some we need to encode P1 rigidity, but it is hard to encode P1 rigidity by both field localization. So we need to go beyond the category of schemes. That's another reason. Okay, so we can use the cube, which is P1 comma infinity. But if we decide to use cube, that means that we need to also define morphisms. And if we define morphisms, then we need to define compositions of morphisms. So we really need to make some category of many compactifications. So we need to introduce some definition, which is given as follows. So SM and SM over S, that's a shorthand for smooth log smooth, is a category whose objects are pairs X comma D, where X is in smooth over S, and D is a strict normal crossing divisor, and whose morphisms are Y comma E to X comma D, such that F Y minus E is inside X minus D. That's it. And I would like to emphasize that we do not consider multiplicities on D, i.e. D is a reduced divisor. Okay, and this category is actually a full subcategory of the following category. So LSM over S is the category of log smooth FS log schemes with the Zariski log structure over K. So log smooth is defined by Kazuya Kato, and FS is some technical condition making the category of FS log schemes more easier to deal with. And there is a functor from smooth log smooth over S to log smooth over S. And for those who know log geometry, I can say the definition like this. So that sends X comma D, the pair X comma D to the compact, the log scheme whose underlying scheme is X and whose log structure is the compactifying log structure associated with the open immersion X minus D to X. So the foundations of logarithmic geometry was developed by Deline, Fartings, Fontaine, Illuzi, and Kazuya Kato. So, and as we saw in the previous slide, this compactification gadget can be effectively studied in its well-developed geometry. So that's the reason why we chose logarithmic geometry to develop the theory of non-A1 homotopy theory. Okay, so that's the story for the replacement of A1. And then, So what is the replacement of GM means what is the replacement of the K-twist. And at the same time, we can ask about what is the replacement of BGM, classifying space of GM. So we can use the compactification. So GM is inside P1, and we can consider P1, 0 plus infinity is a compactification of GM. That's fine, that's totally fine. But one problem is that the morphism, the multiplication morphism, GM times GM to GM, does not extend to a morphism P1, 0 plus infinity times P1, 0 plus infinity to P1, 0 plus infinity. So reason is this is really impossible. There is no such a map. So P1, 0 plus infinity is not a group object if we don't do anything else. So, but probably we want to make this one as a group object. So to remedy this, we consider the blow up as infinity 0 and 0 infinity. And then we consider this morphism. So P1 times P1 to P1 is a birational map. So after some blow up, we may have some map morphism, and that can be done by this blow up actually. And here H1, H2, H3, H4 are strict transforms of the divisors in P1 0 times plus infinity times P1 0 plus infinity. The meaning is the divisors are 0 times P1, infinity times P1, P1 times 0, P1 times infinity. And E1 and E2 are the exceptional divisors. So we have such a map. But still, this blow up is different from P1 0 times P1 0 plus infinity squared. So to view this one as a multiplication, we identify this blow up with P1 plus, 0 plus infinity squared. Okay, but how can you do this? Probably we can invert this morphism, like inverting A1. That's one way, that's okay, but probably there is another way, and another way is done by introducing a topology. So a morphism F from Y, E and to X, D is a dividing cover if it is a proper surjective log et al monomorphism. So log et al is introduced by Kato also, and proper means Y to X is proper, surjective means Y to X is surjective, so Y to X is a surjective morphism of schemes, and monomorphism is monomorphism in the category. So it turns out that this is equivalent to the notion of log modifications defined by Kato if we just consider Zariski log structures. So Kato considered also eta log structures, but if we just restrict to Zariski log structures, then they are equivalent. And moreover, the blow up in the previous slide is an example of a dividing cover. And why? Why this implies inverting that morphism? Because the key point is a dividing cover is a monomorphism. So suppose we consider the check descent condition. The check descent condition is the same as just invariance condition. And we can show that the hypercover descent condition is equivalent to the check descent condition in this case. So that means that hypercover descent condition is equivalent to invariance condition. So if we just introduce the topology in our category, then this morphism, any dividing cover is automatically inverted. So this is the reason why we use this topology. So that's the dividing topology. But anyway, we want to generalize Voevodsky's construction. So we want to generalize the synergy topology also. So I will give a definition. So a morphism y comma e to x comma d is strict if E is just isomorphic to the pullback y times xd. And a morphism f is a strict Nisnevsky cover if f is strict and y to x is a Nisnevsky cover. And the associated topology is the strict Nisnevsky topology. Okay, and then the dividing Nisnevsky topology is the smallest topology generated by strict Nisnevsky topology and the dividing topology. And this is the topology we mainly use in our paper. And probably for information, I can say something about CD structure. So the strict Nisnevsky CD structure is the collection of squares of the form such that all the morphisms in the square are strict. And the square y prime y x prime x is a Nisnevsky distinguished square. So these are strict and just comes from a Nisnevsky distinguished square. And on the other hand, the dividing CD structure is the collection of squares of the form empty set in the left side and y comma e to x comma d f such that f is a dividing cover. So we can make such a CD structure. And one theorem we have is that the dividing Nisnevsky CD structure is complete, quasi-bounded, and regular. So we introduced quasi-boundedness because the dividing Nisnevsky topology is not bounded. Anyway, the Brown-Jordan property is still satisfied by every complete, quasi-bounded, and regular CD structure. So we can use this one. Okay, so by introducing this one, we could replace GM and we can consider the group object. We can consider GM as a group object. Okay, so I will say something about K-twist. So P1 is already compact, so we do not replace P1. And recall that there are two equivalent definitions of K-twist in DMK. So Z1 is M point to P1, -2. So point to P1 means we consider a complex Z transfer point to Z transfer P1. And we consider the motive associated with this complex. But that's the notation. On the other hand, we can consider Z1 as a point to GM, -1. And these can be replaced by the following, like Z1, M point to P1 is the same, but Z1 is M point to P1, 0 plus infinity, -1. And we also have gamma x, d Dinis is your shorthand for dividing Nisnevich. A Dinis P1, 0 infinity. So dividing Nisnevichification makes this one as a group object. So we can consider the cohomology of this one, and this is isomorphic to gamma x minus d, omega x minus d star. And of course, we cannot formulate this one without dividing Nisnevichification, because without this one, P1, 0 infinity is not a group object. And also in our Motivic homotopy categories, using box invariance and Mayer-Vittorius, we can show that P1 is in homotopy category isomorphic to S1 smash with P1, 0 plus infinity. That can be done by using probably two Mayer-Vittorius squares. Okay, so far we have discussed about replacement of A1 and replacement of GM, replacement of T-twist. And then we also need to replace finite log correspondences. So we also discussed about replacement of topology. So finite correspondences is defined in smooth over K. And we want to extend this one to log smooth over K. And there may be some other definition, but we just need one nice definition. So the definition of one possible definition is as follows. So here I will just write the definition for smooth log smooth over K, and this can be extended to log smooth over K by a similar way. So if x, d and y, e are smooth log smooth over K, an elementary log correspondence from x, d to y, e consists of two parts. Part one is exactly the same as the definition in dm. So on integral subscheme z of x times y, that is finite and surjective over x. And part two, so part one is exactly the same, and part two is new. A morphism, zn and zn times xd y, e of fs log schemes, where zn is the normalization of z. So here, this morphism is not described by the way I explained before, because Zn may not be smooth. And Zn times xd may not be a strict normal crossing divisor. So this is really a morphism of fs log schemes. So not just a morphism such that g Zn minus Zn times xd is inside y minus e. And a finite log correspondence is a formal sum of elementary log correspondences. And L core x, d, y, e is the free abelian group of finite correspondences. That's our definition. And if D and E are empty sets, then part two is nothing. So we can compare with user finite correspondences. So L core x, empty set, y, empty set is just core x, y. On the other hand, the part two allows us to make elementary log correspondences composable. Without part two, we cannot compose elementary log correspondences. We really need this extra part. So we can consider this construction. So I'd like to emphasize that K is a field with a trivial log structure. We do not consider log point in this paper, in our paper. So there are three main ingredients as before: box to point instead of A1 to point, and dividing Nisnevich topology instead of Nisnevich topology, and finite log correspondences instead of finite correspondences. So use finite log correspondences to form the category of pre-sheaves with log transfers, and then form the category of dividing mismatched sheaves with log transfers. Here, we need something. So in Voevodsky theory, to show some nice properties like category of mismatched sheaves with transfers is a gross-ending abelian category. He needed to prove something, and that's the same here. So we can show that the category of dividing mismatched sheaves with log transfers is a gross-ending abelian group, and we need some argument. This is not automatic. And then invert box to point in the category of dividing mismatched sheaves with log transfers to obtain log DM effective K. So that's it. And if we apply P1 stabilization, then we can obtain log DMK. But we do not know the cancellation theorem. So it will be very helpful if we can prove cancellation theorem. And I'd like to also say that there is a comparison between log DM effective K and DM effective K. And Federico Binda will talk about this tomorrow in more detail. There is an alternative approach, motives with modulus by Kan, Miyazaki, Saito, Yamazaki. So, smooth log smooth over K means X is smooth and this divisor with just multiplicity 1. But in their paper, the divisors can have some multiplicity, and the theory can be more complicated because of this existence of multiplicity. So probably philosophies are similar. Okay, and then you can consider log SHS similarly. And here we don't need finite log transfers, but just form the category of dividing mismatched sheaves, and then invert box to point, and then apply P1 stabilization. And then we get log SH. Okay, so since we have some candidates of non-A1 homotopy theory of schemes, we can consider some representability questions. So about to represent things in log H. So log H is without P1 stabilization, but just S1 stabilization. And log SH, we may consider the following steps. Extend the cohomology theory to FS log schemes. So for example, suppose we have HH or THH, and first we need to know what's going on for log schemes. That's also a non-trivial task. And then prove box invariance or cube invariance. That's also another non-trivial task. So probably I can say some examples we know. So if X, D is in smooth over K, then we can consider logarithmic differential forms, omega J, X, D over K. This is good, and this can be extended to log schemes also. And actually, this is a dividing mismatched sheaf with log transfers. So these are representable in log DMK, not just log SHK. And also we can consider log HHN and log HC. So
where S is a log smooth FS log scheme over a field of characteristic 0 by using Hochschild constant Rosenberg theorem. But but the way is we first show HHN of S is representable in our category when S is a scheme with a trivial log structure, and somehow this is so this is kind of a definition. So we define log HHNS that is extension of HHNS. So okay, and then we have some questions and work in progress. So can we represent log HHN, log THHN? So actually, the definition is given by Rogones. If R is a pre-log ring, so pre-log ring is some pre-version of a log thing, and actually we can consider some logification such that log HH is equivalent under this logification. So, but this is on for pre-log ring, not for log schemes. On the other hand, log HHN and log HC N is defined by Olson if S is a log scheme, probably a fine log scheme. So we have some extension. So in the previous slide, we have these two things, two steps, and probably for number one, we can just use these two. But the question is, of course, what is, how can you show cube invariance? That's another question we need to work. And I'd like to say that I don't know whether these two definitions are the same or not, equivalent or not, if S is a spectrum of a pre-log ring or spectrum of a log ring. Also, we can define K theory. So here S is an FS log scheme, and Kn log S is defined by Hom log SHS S plus sigma n KGL, and this T spectrum KGL, the T is S1 smash with P1, 0 plus infinity instead of S1 smash with GM. So T spectrum KGL is defined by cube localization of Z times GR, comma, dot, with a certain bonding map. But this is similar to the original bonding map of Motivic. And so this is our definition of logarithmic K theory. And one question, one conjecture we can ask is Kn of X is isomorphic to Kn log of X if X is a scheme with trivial log structure? If we can know this one, then we can consider this logarithmic K theory as an extension of a user K theory. So proving box invariance may or may not require some extra work. From our experience, we expect that projective bundle formula helps to prove this. And more questions. So what is log dm effective K Zn MA1? So this is a non-A1 invariant singular homology of A1, which should not be isomorphic to Suslin singular homology. And we expect that there is a relation between this group and big gram big complex, but we don't know how to formulate a precise statement. And cancellation theorem, as I told before, that's also an open question. And another open question is, can we list axioms for cohomology theories of schemes such that any cohomology theory with these axioms can be canonically extended to log SHS? If we can solve this problem, then we can automatically solve all the representability questions, because we just need to plug the cohomology theories in this frame. So probably these are some axioms that should be satisfied already. So P1 rigidity, inception descent, and these two are not enough. So 3, descent for Cartesian squares of the form. So blow up Zx, Xz, but here we require that I is a regular embedding. So this is a 3 is smaller than CDH distinguished squares, some part of CDH distinguished squares. And for example, K theory satisfies all these 3 properties. So our question is, are these enough? Do we need more axioms? Okay. So we defined log DM effective, and I'd like to explain another construction of DM log effective. So let S be a scheme without log structure from now, and recall that there is a free safe functor smooth log smooth over S to log smooth over S. And log smooth over S contains more things, like some scheme with toroidal singularities. So probably it's easier to define theories for smooth log smooth over S, and then probably we can extend to log smooth over S by some machine. And I'd like to explain what is this machine. So the theorem is as follows. So cube invariance plus dividing mismatch descent in log smooth over S. This data is equivalent to Pn, Pn minus 1 invariance for our n, and strict mismatch descent in smooth log smooth over S. So if we know some cohomology theory satisfying Pn, Pn minus 1 invariance for our n plus strict mismatch descent, then we automatically extend this theory to log smooth over S. And here we regard P1 as the hyperplane of P1 at infinity. So observe that, just for information, both Pn, Pn minus 1 and cube to the n are compactifications of A to the n, different compactifications. They are birational, but not isomorphic. So for proof, the proof is combinatorial. The meaning is there is no transfinite argument. So probably I can introduce the toric picture. So there is a equivalence between this kind of toric picture, toric fence, and normal toric varieties. So for example, P1 times P1 corresponds to the left toric picture, and some blow up 001 P2 corresponds to the right toric picture. And actually that's isomorphic. So that's not equal. I'd like to emphasize that that's not equal, but just isomorphic. And there are 2 blow-ups. And the first and the third log schemes are cube bundles over cube. And we can show that cube bundle does not change the motive. And Q is already, the motive is isomorphic to the motive of point. So their motives are isomorphic to the motive of a point. So then means that the left morphism is an isomorphism if and only if the right morphism is an isomorphism of motives. Okay. And I would like to emphasize that the left morphism is not a dividing cover, and the right morphism is a dividing cover. And we can use Mayer-Vittorius several times, not just one time or two times, but several times to deduce that this double star is an isomorphism if and only if a star is an isomorphism. The star corresponds to the right morphism. Double star corresponds to the right morphism, and double star corresponds to the left morphism. And so these two are just equivalent. So suppose we know dividing descent, then we know star, so we know double star. Okay, so star is equivalent to double star. And suppose we have box invariance and dividing invariance. Then by the previous slide and using Mayer-Vittorius, so the left morphism is an isomorphism because of 2 double star, and the right morphism is an isomorphism because of star. So these two morphisms are isomorphisms of motives. And since motive of box squared is isomorphic to the motive of point, this shows that motive of P2, P1 is isomorphic to motive of point. Okay. So this shows that if we know box invariance and dividing invariance, then we know that P2, P1 is contractible. On the other hand, suppose we have Q invariance and P2, P1 invariance. Then the morphism in the picture becomes an isomorphism of motives, since the right log scheme is a box bundle, cube bundle of cube. Here, H1 is a hyperplane and is an exceptional divisor, the exceptional divisor. And then we can use Mayer-Vittorius to show that this morphism M blow up 00A2, H1 plus E2 M A2, H1. But that's some part of this, some open part of this morphism in the picture is an isomorphism of motives. So, okay. Hence, assuming Q invariance, these two are equivalent. This is the way to show this theorem in some special case. In some low dimensional, so this is a low dimensional argument. And then we can generalize this argument to arbitrary n by induction. And this concludes that cube invariance plus dividing descent in log smooth over S if and only if Pn, Pn minus 1 invariance for or n plus strict descent in log smooth over S. So here still we have not achieved smooth log smooth over S. Log smooth over S still. And to achieve smooth log smooth over S, there is a machine like if F is a theory on smooth log smooth over S, you can consider iota lower sharp F given by colimit Fy, where Y runs over all dividing covers of X such that Y is in smooth log smooth over S. And then we can show that F satisfies Pn, Pn minus 1 invariance for n plus strictly infinity descent, if and only if I lower sharp f satisfies the same thing. So from this, we can obtain our theorem about another construction. So that's all I want to say today. Thank you very much for your attention.
Okay, thank you. We all thank Doosung for his nice talk. And now it's time for questions.
I have a question. Can you hear me?
Yes.
So it seems that you don't have an explicit box resolution like the Susslin complex for the classical DM effective, or do you?
We have this. So we have so in some special case, like yes. So we have some functor, and we have some thing, which is used for in many cases, but not useful for resolving Z transfer A1.
Is it an abstract functor or concrete
like abstract
one?
functor? We have some functor like similar to C star.
Similar to C star.
Yeah, C star and sin, like C star of F.
Okay. How do you get this this functor?
So the way is we consider f x times cube to the n, but that's not enough. We need the category of admissible blowups to x to the cube, x times cube to the n. Admissible blowup is isomorphism on the open part, and we need all admissible blowups. So the formulation is like colimit fy, and y runs over all admissible blowups of x times the box to the n. And we can consider this one as a sin, but problem is that we need resolution of singularities here. Otherwise, we cannot say that the colimit is a filtered colimit. But so we can use this thing to compare log DM and DM.
And then you can also compute the analog of singular homology, I guess, with this complex.
Yes, but not for motive of A1, because motive of A1 is tricky. So motive of A1 is already cube invariant, but not strictly cube invariant. And sin construction, the naive sin construction is not helpful. So we can take like infinitely many, but that's untractable. The infinite many repetition of sin and localization, that's possible, but that's untractable, so that's not useful for computation.
I have a question. Does your theory extend to type 1 cohomology theories and give you the same thing back?
Sorry?
At the beginning of your lecture, you talked about type 1 cohomology theories that are A1 invariant.
Yes.
Does the theory reproduce those, or does it change them?
Yes, so assuming perfect field of resolution of singularities. So DM is a full subcategory of log DM effective. DM effective is a full subcategory of log DM effective. So we produce that, assuming resolution of singularities.
So it has more objects?
Yes. So for example, Hodge cohomology is representable in a log DM effective, which is not representable in DM effective.
Thank you.
Can I ask a question?
Yes.
So you mentioned a tal cohomology with ZP coefficients, right? So
yes.
Also FP coefficients. And I know that there have been some there was some recent work of Katharina Hubner on the tame site, and like they define sort of a tame version of the étale site, so to speak, and the cohomology. I mean, there are some results of on the FP cohomology of in that sense. So, is it related to this F sort of log extended FP cohomology that you get here?
Actually, I don't know about that, but so here the log extension can be, for example, done by Kumar et al. Cohomology.
Aha, okay, yes.
Probably there may be related to that, but I don't know.
Mm-hmm. So in your case, this is just Kumar et al. Cohomology of FP.
Yes.
Mm-hmm. Thank you.
All these Lefschitz Zeichen cohomology of FP also. But probably that's not, I don't know. That's not Q invariant, so probably Kumar et al.
Okay, last chance for other questions.
Maybe just a remark. Nisiol has defined as extended K-theory to log schemes.
Yes.
And then you could ask that is your K-theory, your KGL agree with her K-theory?
No, they are not. So Nisiol's K-theory is, I guess, not Q invariant.
Okay. Then end of the question.
Okay, so we thank Doosung again for his nice talk and answers to the questions. And well, that's all for today. Have a nice evening. See you all tomorrow.